fascinating life story of the stars. We've learned that everything on Earth, including ourselves, was formed from the chemical elements from some unknown and distant star.
Before the early part of this century, the story of the internal structure of the stars was still a mystery that was unsolved. Now, we did know what the stars were like on the outside, at least in a sense, because we could see the light that the stars emit. But we had no idea really what the stars were like deep within at their cores. We couldn't see into the centermost part of the stars, not even for the nearest star, our own sun. Our view was just blocked by the material that makes up either the sun or the stars, and so the secrets are really hidden from view. But we did know how, from the laws of physics, gases should behave, and so from that we could calculate how the material inside the star must itself behave. Well, from that we also could calculate what effect that material would have on the outside of the star, the light that it emitted. And then, of course, we could compare our theoretical picture of the stars, what they should be doing from our understandings of the laws of physics, and what they actually are doing as we see the stars in the sky. Of course, the real problem was that up until the early 30s or so, no one really knew what the source of energy in the stars was. But by the time that Einstein and Eddington and Bethe and Critchfield realized that thermonuclear fusion was the energy source behind the stars, we were well on our way to understanding how the stars were built and how they evolved. And of course, through this understanding, we can also tell what happens during the process of transformation from hydrogen into helium to the star as its hydrogen fuel is exhausted.
Early in the evolution of a star, isotopes of hydrogen and helium are formed in a process known as the proton-proton process. The proton-proton process begins when a proton, which makes up the nucleus of a hydrogen atom, collides with another proton. One of the protons that makes up the resultant nucleus loses its positive charge and becomes a neutron. The result is the formation of one of the isotopes of hydrogen, hydrogen-2 or deuterium. When an additional proton collides with the proton and neutron of the deuterium nucleus, a helium-3 or a light helium nucleus is formed. When two helium-3 nuclei collide, they can combine to form a helium-4 nucleus, in the process liberating two additional protons. The helium-4 nucleus, composed of 4 particles, 2 protons and 2 neutrons, is the final product of the proton-proton process. This pattern, from lighter to heavier element formation, is a progression from fewer to greater numbers of particles in the nuclei of atoms.
The proton-proton reaction is the simplest cycle that the stars use to transform hydrogen into helium. And through this conversion, the star produces the energy that allows it to shine and that, of course, keeps it in balance against the force of gravity that's always pulling inward. Stars spend about 90% of their lives in this hydrogen-burning phase. It's the normal state of a star's life, and it's called the main sequence phase of the star's evolution. But before theoreticians could determine what would happen when the star left this stage and grew older, well, it would be necessary, in order to answer that question, to understand the incredible variety of the stars we see around us. They differ tremendously in color and in size and in brightness. Well, what could possibly cause this variety of stars? Stars which would otherwise have to be considered the same. After all, they're under the same state of equilibrium, and they also are using essentially the same method of producing their energy, thermonuclear fusion. Well, the answer to this puzzle is found with the spectroscope.
One of the great breakthroughs in the history of science began when the spectroscope was first used on the stars as well as the sun. And it was discovered that they were all composed of the same types of elements found on Earth. Then, about 1900, Planck and Wien found that the temperature of a hot glowing object determines the color of the light it radiates. As the temperature increases, the color can change from red to orange to yellow to blue. A star such as our sun, with a temperature of 6,000 degrees Kelvin, glows brightest in the yellow region of the spectrum. Every star's temperature can be determined by the color which glows most brightly in its spectrum. High temperatures produce short wavelengths of light, blue or violet colors. Red or orange colors are longer wavelengths, generated by lower temperatures with less energy. The analysis of starlight advanced further when two astronomers, Hertzsprung and Russell, found that the temperature of a normal star affects its absolute luminosity or brightness. The hotter the star, the brighter it glows. Around the 1920s, Eddington discovered that a normal star's luminosity or brightness is also related to its mass. The more massive star is hotter and brighter. As a star evolves, its mass will determine its temperature, and the temperature in turn determines its color and brightness. Another important advance occurred during the 1930s and 40s, when physicists discovered how a star's mass controls its temperature. This is a cross-section of a normal red star, showing its layers of matter. Each layer is pulled in toward the center by the star's gravitational forces. The combined weight of the layers exerts a crushing pressure within the star's core. This enormous pressure causes a temperature of millions of degrees. Here inside the subatomic spaces within the core, the electrons and nuclei are kept apart by the ultra-high temperature, which accelerates them to an ultra-high speed. If the nuclei collide at this speed, they often fuse together, and part of their mass is released as energy. This is only a microscopic space in the center of a star, but such countless bursts of nuclear energy throughout the star's core create the awesome power of a star. Energy from the core working its way outward through the star causes the light, heat, and other radiations streaming from the red star's surface. This type of red star is the least massive star that can exist. A celestial body with less mass than such a red star, for example, a planet or a moon such as snow-covered Titan, does not have enough mass to generate the gravitational pressure needed to smash the nuclei and release their energy. So its surface remains cold and dark. A very massive blue star is dramatically different. Comparing its diagram with a less massive red star shows how more layers of matter pulled in by gravitation creates more pressure in the core, causing even higher temperature and density. This fuses together the nuclei at an even faster rate than for the red star, releasing huge amounts of energy. The more massive blue star is hotter and brighter as a result of this energy. Because its nuclear fuel is consumed at a faster rate, the star's life is shorter. More energy pushes its matter outward, causing its larger size. Scientists can now explain why stars with the same mass have the same properties, while stars of a different mass have different properties. Mass, the amount of matter an object contains, determines most of the star's properties, including the rate it produces energy, its size, gravity, and inertia. A star's lifespan, its temperature, and luminosity are all determined by its mass. The nature of stars, which had long been a mystery, can now be explained by the same physical laws which explain the nature of things on Earth.
A star's mass is what gives it its character, and we now know that it's the differences in mass that explain the variety of main sequence stars that we see. But what happens when the thermonuclear fuel of a star runs out, when it's gone? It's harder and harder then for the star to maintain that balance against gravity. Well, for the astronomer to answer this question, to even begin to answer this question, it's necessary to know a great deal more about the star. In fact, we have to know exactly what's going on in the star throughout, from the surface to the center. All the important things, temperature, pressure, and density, have to be listed. Well, such a list is actually called a model, a stellar model, and astronomers construct these in order to describe the stars. Well, it's really just a list, then, of all the basic characteristics throughout the star. But such lists are a vital part of our understanding the evolution of stars.
These mathematical equations describe how mass, pressure, temperature, and luminosity vary outward from the center of a star. The electronic computer has been critical in solving these equations. Without the use of a high-speed digital computer, much of the progress made in the last 20 years would not have been possible. Within these equations of stellar models are additional quantities such as chemical composition, density, opacity, and the rate at which energy is generated. By altering these factors, it is also possible to compute stellar evolution, to see what happens to a single star as it ages. To calculate theoretically the effects of stellar evolution, it is necessary to change some of the conditions in the stellar model of the star, to match changes occurring in the star itself as it evolves. The most important change is the chemical composition.
As the hydrogen's depleted in the core, you're left with a helium core. This core it's still hot, so it's radiating energy, but it doesn't have a nuclear source of this energy, so it begins to collapse again. The principal energy source from the star is still hydrogen burning, but it's now in a thin hydrogen burning shell around this helium core. At this point, the hydrogen burning becomes very intense and the envelope begins to expand. The star leaves the region of the HR diagram that we call the main sequence and moves over to the giant branch. It becomes very expanded and very red. Eventually, as hydrogen is converted to helium in this shell, the helium shell grows and you reach a point where the central temperature and density of this helium shell is sufficient to begin burning helium through the triple alpha process.
When two helium-4 nuclei collide, an 8-particle nucleus, beryllium-8, is formed. But beryllium-8 is so unstable, existing for only 1/4 of a second, that it almost instantly breaks down into 2 helium-4 nuclei again. However, the combination of 3 helium-4 nuclei creates a stable, heavier element, carbon-12. Because of its stability, carbon-12 functions importantly in the formation of still heavier elements. The collision of a carbon-12 nucleus with another helium-4 nucleus produces the heavier element, oxygen-16. This alpha process is also partly responsible for the creation of still heavier elements, such as neon, magnesium, and silicon.
As a star ages, the temperature in the core goes up, and throughout this time, the lighter atoms make up the star are being transformed into heavier atoms. And it's the mass of a star that controls how hot it is deep in the center. And it's that core temperature that in turn controls where we wind up at the end of our cycle of transformations. What element is going to be at the end of the line? Well, in the most massive of the stars, we find we go through a long sequence from hydrogen to helium, and helium to carbon, and carbon all the way down through a series of others to iron. But iron is the end of the line. And the reason for that is we just can't get enough energy out of changing iron into anything else. And so there, the thermonuclear cycle stops. Well, we find the iron then and all of the other elements before it in the stars, and these are the same things that we find in the planets, even in the Earth, in ourselves for that matter. And we now know where all these things come from. They come from the stars. But it's the abundances of these elements that also cause a little bit of a mystery for us. For instance, we look and we see that some of them are very, very common, and others are quite scarce. And of course, we have to ask, why would this be so? Well, we now feel that the most common elements, things like nitrogen and carbon and oxygen, are produced by the long-lived reactions, things that go on for a long time in the cores of stars, like the triple alpha reaction. The rarer elements, on the other hand, gold and silver and so on, these things are probably produced in a variety of processes that take place when, for instance, a star explodes in a violent catastrophe that blows most of the star off into interstellar space. Well, we realize that in the beginning, the matter that made up the universe was just hydrogen and helium, two things, just those two elements. Everything else that we see was forged in the stellar interiors later. Some of it even at moments of cataclysmic explosions of stars, when this material is blown off back again into interstellar space. And as that occurred, of course, gradually it was gathered back together again to form new stars, second-generation stars, and third-generation stars, and so on, with their planets, and their people, and everything else. And we ourselves, then, are stardust, and our lives are intimately connected with the life cycles of stars.
It is the death of stars, therefore, that enriches the universe with the chemicals that eventually made life possible. But it's equally important to understand the birth of stars, because it is as a byproduct of stellar formation that planetary systems such as our own solar system are created. Blue stars are known to be the youngest in the galaxy. Because they are only a few million years old, they are still clustered together near the clouds of dust and gas from which they were born. Photographs show that as these clouds become smaller, they become darker, which suggests that they are collapsing to form still other stars. No one has actually witnessed stellar birth, but theoreticians do have an idea of how it probably occurs. In theory, when a cloud of gas and dust reaches a certain density, it could collapse or fall together under its own weight. It might fall into one or more separate units, forming single or multiple star systems, perhaps with planets. The volume shrinks a billion times. The cloud becomes hotter and denser as it continues to fall in toward itself. At the center of the sufficiently massive cloud, the density and temperature might be so high that there are collisions between the atoms of hydrogen, and some of these collisions are energetic enough to produce nuclear reactions. The release of energy creates a gas pressure that stops the collapse of the cloud. Some clouds are unstable and move in and out or pulsate as the forces of gas pressure and gravity seek to adjust themselves. Eventually, after millions of years, as the hydrogen burns in the furnace of the interior, a stable cloud of gas, a stable star, one of nature's most magnificent inventions, is born.
All the evidence we have on star formation indicates that one star isn't formed by itself, but rather that they form in big bunches all at once, what we call star clusters. These clusters can number anywhere from a few dozen stars up to many hundreds. We know this is true because we see stars being formed right before our eyes at the present time. For example, here in this picture of the Orion Nebula, we see the cloud of gases, that's the green stuff, You see the stars, 4 bright ones there in the middle and a bunch of little fainter ones around the outside. Now the stars in there which are going to end up like our sun are not those big bright ones. Those are a special class of heavyweight stars. But it's one of those faint ones out there which might possibly be a future sun with planets.
Within the Orion Nebula, astronomers can see dark areas of cool gas which they believe are condensing into stars. These clouds of gas are basically composed of 90% hydrogen and 10% helium, with only a trace of heavier elements and dust grains.
One of the things that you always have to keep in mind when thinking about the formation of a star is that there's going to be a certain amount of rotation. You start with a big diffuse cloud of gases, and we're now talking about a subsection of what was once the big interstellar cloud, just a little piece of it that's going to make one star, or possibly a double star. Anyway, there's a certain amount of rotation, and as the cloud contracts down more and more to form a star, the rotation is going to speed up. If there's enough rotation there, the thing may split before getting down to the size of a star, and you end up with a fairly close double star, for example. In the case of the sun, it's thought that there wasn't that much rotation, and it contracted down to something like the, well, not right down to the size of the sun today, but down to something like the orbit of Mercury with a radius of a few million miles. And at that point, the sun was spinning pretty fast, and maybe some stuff spun off from the equator, or maybe there was just some stuff that didn't quite fall in and was circulating there around the equator of the sun, and that material formed the planets eventually. And it would seem most likely to be a question of just how much rotation is present. A lot of rotation, you'll get a double star. Not so much, you're likely to get a single star with planets. If there's very little rotation, you might get a single star with no planets.
The exact effect of angular momentum on stellar and planetary formation is far from understood. There are still many mysteries to be explained, which may be accomplished with new observational techniques. Astronomers believe this cosmic cloud of gas and dust to be a maternity ward of stars. Here, condensations are forming and the force of gravity is attracting more particles. For several million years, the nucleus of each star will continue to become hotter as the star contracts. As these young stars evolve towards the main sequence phase of their lives, they are first detectable by their emission of large quantities of infrared radiation.
We've only recently learned to detect and analyze the infrared radiation that comes to us from the stars, but it is of unquestionable importance to us because it helps us understand the formation of stars. Now, the formation of a star is more than simply a progression from a large, thin cloud of gas to a much smaller and denser star. It's also a progression of an environment from a few degrees above absolute zero in temperature to something that's thousands of degrees Kelvin at the surface. And until the star gets that hot, that is when it's cooler, it gives off most of its light in the infrared. Well, the same would be true with any object that's only a few hundreds of degrees in temperature. Now, even after the star reaches a higher temperature and gives off visible light, it's still surrounded by dust, and this dust is left over from the cloud from which the star originally condensed. Well, until that dust is blown away, it absorbs visible light from the star and re-radiates it at infrared. So that's two reasons, then, that we must look into the infrared to see what's going on. And finally, at the cool temperatures that are typical of the formation of a star, the gas is in molecular form rather than in atoms, and most of the spectra of molecules are consisting of radio